The screen you are looking at is a carryover from the last video, part 4. The new video, part 5, will start soon. I want to speak about how to go about proving identities and do some examples. There's no specific set of instructions for proving trig identities. Each identity has its own unique composition, and proving identities requires a modest amount of insight. Some risk-taking is necessary when making substitutions, since some substitutions, which may make sense at the time, do not yield the result you expected. So you have to start again and take a different tact. One way to start is to see if changing everything into sines and cosines helps. On this screen now that you are looking at, which is part 5, we will prove two identities. The number 1 is to prove that the cosine of x times the cosecant of x times the tangent of x is equal to 1. Well, let's see what we can do here. The cosecant of x is 1 over sine x. The tangent of x is equal to the sine x over cos x. Now, if you look at the numerator and denominator of this expression, cosines x are found at the numerator and in the denominator. So, in the same way, the sine of x is also in the numerator and denominator, which can cancel out, and the result is equal to 1, and consequently is equal to the right-hand side, and thus proves the identity. In the second one, prove the cotangent of x plus the tangent of x is equal to twice the cosecant of 2x. Now, the cotangent of x is cos x over sine x, and the tan of x is sine x over cos x. If you add the two together, you get cos squared x plus sine squared x, which is equal to 1 over sine x over cos x. Now you have to multiply top and bottom by 2, and when you do that, you get the identity proved. One application of identities is in the solution of trigonometric equations. Concentrate on the second example that I have here, where the equation has two functions, sine x and cos x. We need to change the functions so that they are just either sine x or cos x. I have decided to change the sine squared x into 1 minus cos squared x and substituted. So what you end up with is 1 minus cos squared x plus cos x equals 1. When simplified, you end up with a quadratic equation. Cos x plus cos squared x equals 0. Factoring, we get cos x times 1 minus cos x equals 0. And solving for this, you end up with cos x equals 0 and cos x equals 1. And the solutions are 0, 90 degrees, 270 degrees, and 360 degrees. The angles that we want between 0 and 360 degrees. First of all, the identity sine of a plus b is equal to the sine of a cos b plus cos of a sine of b. We will also make the substitution that if x is equal to a and theta is equal to b with r a coefficient, then r sine x plus theta is equal to r sine x cos theta plus r cos x sine theta. Check the board carefully and make a note that we have the proper substitution for a, x, b, theta, a for x, and b for theta. You will be given problems in which a times a sine x plus b cos x is equal to some constant c. In this example, a, b, and c are numbers. We can refer to those quantities, because they are numbers, that they are parameters. The parameters are, and that simply means that these are numbers. So, for example, 2 for A, 3 for B, and maybe 1 for C, or whatever would be such an example. It is required that it be converted to an equation of the form r sine x plus theta. To a sine function in the form of r sine x plus theta. By comparing the identity with the given equation term by term, note very carefully that a is equal to r cos theta and b is equal to r sine theta. The variable theta and r are required. That is to say, r and theta must be determined. R will go in this position when we find it, and theta will go in that position when we find it. Note the following: that a squared plus b squared is equal to r squared cos squared theta. Here's a, and so when that's squared, it's r squared cos squared theta, plus r squared sine squared theta. R squared is a common factor on the right-hand side, and if we extract it and rewrite it, we end up with r squared multiplied by cos squared theta plus sine squared theta, and we have shown you earlier that that is equal to 1, so r squared times 1 is 1. And we've come to the conclusion that r can be found by calculating a squared plus b squared equals r squared, and r is equal to the square root of a squared plus b squared. The positive root of r is the one that we use. This does not have a negative value for r. Now, the other part of the expression that we were going to determine was theta. Well, from this main statement, which I will block in, we can determine the value of theta. B over A is equal to r sine theta divided by r cos theta, r over r, 1. So we have sine theta over cos theta, and that's equal to the tangent of theta. Having determined that the tangent of theta is b over a, we can conclude then that theta can be found by determining the arctan of b over a. The quadrant for theta is chosen by checking the sign of sine and cosine. If r is always positive, then a and b can either be positive or negative. Then the reason why a and b are positive or negative is because of cos theta and sine theta. Let's look at an example to see how the work above applies to it. We want to change the equation 3 cos x minus 2 sine x equal to 1, where x ranges between 0 and 3 degrees. What we'll want to do is, first of all, rewrite the given equation so that the terms correspond in the same order as what were found in the identity that I wrote earlier. Therefore, this is equivalent to minus 2 sine x plus 3 cos x equals 1. It is clear then that r cos theta must be minus 2 and that the r sine theta is equal to 3. Since r is always a positive number, as I have said, then the cos of the angle is negative and the sine of that same angle is positive. You should come to the conclusion that the only place theta can be in the 4 quadrants of the Cartesian plane is that it is in the 2nd quadrant, and in the 2nd quadrant only. Tan theta is therefore equal to the sine of theta, which is 3 over minus 2, or minus 1.5. Using the calculator, theta is equal to the arctan of negative 1.5. If you place negative 1.5 on your calculator and use the inverse function, you'll find the angle given is in the 4th quadrant. But that cannot be the correct angle, so you have to make the necessary adjustment. In fact, you find that it is equal to negative the value of 56.31. A 4th quadrant angle. You must come to the conclusion that the required angle is in the 2nd quadrant, which makes theta equal to 180 degrees minus 56.31 degrees, which is equal to 123.69 degrees. Also, r can now be found as equaling the square root of a squared plus b squared, which is equal to the square root of negative 2 squared plus 3 squared is equal to the square root of, and that amounts to 3.606. We now have the form of this function in terms of sine alone, and it is written as follows: 3.606 sine x plus 123.69 degrees is the amount equal to the left side of the given problem, and this therefore is equal to 1. Our job here is to find out what in fact the value x is that makes this statement true. We continue to determine what x equals by dividing both sides by 3.606 as one of the required steps in obtaining all the angles for x for which the statement is true. So it's 1 divided by 3.606, which amounts to 0.2773. Now, the way that we find what the angle for sine is equal to is to take the arc sine of the right-hand side, and x plus 123.69 degrees is equal to the arc sine of 0.2773, which you find if you use your calculator is equal to 16.10 degrees. Now, the other possible values for which the sine of this angle is equal to this positive number would have to be located in the second quadrant and first quadrant alone. And since we have to determine all the values between x between 0 and 360 degrees, there is somewhat of a search that has to be conducted. So we find that x plus 123.69 degrees can equal to 16.10 degrees, first quadrant. It could be 180 degrees minus 16.10 degrees, which is the second quadrant. So let's take a look at what occurs when we take 16.10 as a value. X equal to 16.10 degrees minus 123.69 degrees. We can see that this is a negative number, and in the next case, x would equal to 180 degrees minus 16.10 degrees minus the 123.69 degrees. And when this is calculated, we find that the answer is 40.21 degrees. For 42.1 degree is an answer we will save. Sorry, I meant to say 40.21. This one we'll save. Finally, let's have a look at this other one. X is equal to 360 degrees plus 1610 degrees minus 123.69 degrees. And this amounts to, after you simplify, that is equal to 252.41. And we will save that. And if you continue to try all these other related angles, you'll find that you're going to end up with answers, but that they will be outside of the domain that x is restricted within. So we have the two answers, 40.21 degrees and 252.41 degrees. You'll notice that in the equation where I had a cos theta plus b sine theta is equal to c, that you cannot have a ratio when you divide the angle for sine greater than 1, because there's no sine nor cosine of any angle where the value of such angles is greater than 1. Here is an alternate solution that has a very direct approach to getting the solutions we want. We want to introduce a couple of identities. That is, that the cos of x is equal to 1 minus tan squared 1/2 x divided by 1 plus tan squared 1/2 x. For sine of x, this is equal to the identity 2 tan 1/2 x divided by 1 plus tan squared 1/2 x. Let tan 1/2 x equal the transition variable t. Therefore, cos x is equal to 1 minus t squared divided by 1 plus t squared, and the sine of x is equal to 2t divided by 1 plus t squared. Now we're given that 3 cos x minus 2 sine x equals 1. Within the brackets where cos x and sine x are located, we want to place within those locations the transition variable containing t. So this is 3 bracket 1 minus t squared over 1 plus t squared minus 2 bracket 2t over 1 plus t squared, and that is equal to 1. Now, what is simply necessary here is to simplify the expression and reduce it to an equation as far as possible. 3 times 1 minus t squared minus 2 times 2t equals 1 times, the common denominator is 1 plus t squared. When you do all the simplification and collecting of like terms, what you will end up with here is 4t squared plus 4t minus 2 equals 0, which you can see is a quadratic equation. Let's go one further step and simplify this by dividing out 2, reducing it further. Plus 2t minus 1 is equal to 0. At this point, we will use the quadratic formula to solve this equation, and t is therefore equal to minus 2 plus or minus the square root of b squared, which is 2 squared 4, minus 4 times minus 1 times 2 is plus 8, all divided by twice 2, which is 4. Continuing to simplify this, we have minus 2 plus or minus 2 square root 3 over 4, that is. And finally, minus 1 plus or minus the square root of 3 divided by 2. Therefore, t is equal to negative a half plus or minus the square root of 3 divided by 2. And when you work out the values for t here, you find that they are equal to decimal 36602 or negative 1.36602. So we have then calculated the value for t, which is the transition variable. Obviously, what we want to calculate is the value for x. So taking those numbers for t, we begin again and place those values once for each in that particular location. And so I will continue here to the side. Save that board with the work that's on it. Tan x divided by 2, or half x, is equal to decimal 36602. If you determine x over 2, which is the arctan of decimal 36602, we find that x over 2 is equal to the angle 20.104 degrees. You might try that on your calculator. Now, if x over 2 is equal to that quantity, then multiplying both sides by 2, x is equal to 40.208 or 21 degrees. For the next value of t, negative 1.36602, we have that tan of x over 2 is equal to negative 1.36602. X over 2 is equal to the arc tan of negative 1.36602. And then x divided by 2 is equal to the number 1 negative 53.794. But this is a fourth quadrant angle, and the quantity is negative, but being negative does not correspond with the restriction on x, which has to be positive between 0 and 360 degrees. So if we add 180 degrees, we will place the angle in the second quadrant, which is another position for a negative ratio for the tangent function. Remember that the tangent of an angle is negative in the second quadrant and in the fourth quadrant. And so we have that x over 2, based on this calculation, is equal to 126.206 degrees. Consequently, multiplying both sides by 2, we have that x is equal to 252.41. The same answers we found before.